Hello, welcome to lecture 12, topics of logarithmic and implicit differentiation. These are, if you think about it, you may think these are different types of differentiation, but it's actually not. We're still talking about taking derivatives, but into different contexts, and we'll see what they are about. We're going to start with logarithmic. So what is the idea here? Logarithmic differentiation. This is not a different type of derivative. What this means is that you actually find the derivative of ln of a function instead of the function itself, and you can use that to then find f prime. And why? Why are we doing that? Simply because we normally want to use that when the function f contains many products or quotients or exponents. These are expressions that become simpler when you take a logarithm. So if you can find the derivative of ln of f instead, and then somehow, we're going to see how, but somehow use that to obtain the derivative of f, then that can be good for you. So I'm going to have a little box here that just shows you how it works, but we're going to see it in practice. So suppose that you're trying to find f prime for some function f. That's a complicated expression like this. But we realize that if you take the log, it becomes simpler. As I said, because maybe f contains products or exponents. So imagine that ln of f is ln of a complicated expression, which is a simpler expression to differentiate. So now take the primes of those. Like here, you find the derivatives. And as it turns out, the derivative of ln of f is equal to this expression right here, f of x prime over f of x. Why is that true? Let's just briefly justify this. What would you do if you're taking a derivative of this expression, ln of f of x? Well, this is a composite function. You have an f inside of an ln. So you would call u, for example, this inside, u equals f of x. Then y is ln of u. And you would use the chain rule, which means finding du dx, that is just f prime, whatever that f function is, differentiating the expression u equals f of x. And then also finding dy du. If y is ln of u, dy du is 1 over u. So when you multiply the two things, you obtain this dy dx that you wanted as f prime over u, but where u was f. So this f prime over f is the derivative of ln of f of x. So this justifies the step right here that I circled. All right, so you probably want to always remember this, that ln of f prime is always equal to f prime over f. I have an extra line here, I don't know why. Forget about this one. So now we can continue with from here. F prime over f is equal to simpler prime, whatever that is. We found this. Now you're going to solve for f prime. That was the whole goal from the beginning. So I'm going to multiply this equation by f, obtaining this one. I basically moved the f from the denominator on the left side, multiplying into the right side, and you probably want to then replace, instead of f of x, you're going to write the complicated expression that it was originally. So this is just showing you how the process works. But we usually don't want to think about it this way. We don't want to memorize this formula, for instance. Instead, you're going to be expected to show that you know what you're doing. So let's see this in examples. Here's an example. Using logarithmic differentiation, compute this derivative, which, by the way, you don't have to. You can use the quotient rule for this one if you want. And you have a product in the denominator, so that derivative of the denominator will also need the product rule. It's not an easy function to differentiate. However, because it has a quotient, it has products, and also has exponents, that indicates that we probably want to use log differentiation. So this is how it works. You're going to be calling f, the original function, we're going to need to remember that this is the expression for f. We will plug this into the final expression. But let's take the log. What is ln of f? Okay, when you take a log in the quotient like this, the way that you take a log of this is log of the top minus log of the bottom. And this bottom here, this denominator, is a product of two functions. So we might expand those as a sum. You might want to do that. But keep in mind there is this overall minus sign in front of the second log term. So log of the product is the sum of the logs, but after you distribute this minus, you get this other minus inside. Okay, so you have these logs. We can still simplify this a little bit more with the second and the third terms. Here in the second term, we have log of a term with an exponent. This is the exponent raised to 4. You can bring this 4 outside of the log, like this. And similarly, the same thing can be used in the third one. 5x is going to come outside of the log. And what's left is just ln of e, which is 1. So this third term is just 5x. You should know ln of e to the anything is always that thing, that exponent. So this is ln of f of x. It's a much simpler expression to find the derivative of, which is what we're going to do now. How do we find this derivative? So let's now find ln of f of x prime, which on the one hand, you should always remember is equal to f prime over f. This is the calculation that I did in the previous slide. But on the other hand, let's differentiate the expression that we have above. Well, now this one is, each one is going to take certain rules to find a derivative. For example, ln of tangent of x, that's a chain rule. So maybe I'm going to do this one, but leave the other one as an exercise for you. So I've just underlined that in red. I'm going to do this calculation somewhere separate, like down here. How do you differentiate ln of tangent of x? Maybe let's call that y or whatever you want to call it. And let's call u the inner function, the tan x. So that y is the outer function ln applied to that u. You need to find du dx. The derivative of tangent is secant squared. And you need to find dy du. Derivative of ln u is 1 over u. So the derivative that you want, which is dy dx, of the original expression with respect to x, is the product of these two guys, secant x squared over u, which now you have to rewrite in terms of x by substituting instead of u, you're going to use tan x secant squared over tangent. Which, by the way, we should simplify. This is two trig functions. Secant is 1 over cosine square. Secant square is 1 over cosine square. Tangent is sine over cosine, but because it is in the denominator, really it becomes cosine over sine. So you see that at least the factor of cosine goes away. The final answer for this derivative is going to be 1 over sine cosine. So this whole thing was the derivative of the red term up here. One over sine cosine. Now you have to do the same thing for the next one. It is again ln of another function. Chain rule. At this point, if you have enough practice with the chain rule, for most cases, you should be able to find this derivative directly. You can probably think about it this way. The derivative ln applied to the inner function x cubed plus 2 will just give you 1 over x cubed plus 2. Then you have to multiply this by the derivative of the inner function, x cubed plus 2, which is 3x squared. Together with this 4 outside, that makes a 12x squared. This is the derivative of the second term. So I'm just underlining them so we understand where they come from. But again, if you cannot do this fast at this point, if you don't have enough practice with the chain rule, just do what I just did for the first one. But the third term should be the easiest one. Derivative of 5x is 5. So we have this whole expression now. Just keep in mind this is equal to f prime over f. And we wanted to find f prime. So we have to multiply by f. F prime is going to be f of x times whatever the expression that we just found. I'm just copying this down. And I mean, this is not yet the final answer, but there's just one more step to do. I'm gonna circle this in orange. We have still an f of x in this formula that we already know what it is. We know what the original function f was. This is up here. Tangent over x cubed plus 2 to the fourth e to the 5x. That's why I said keep this. You're gonna need to plug this into the final answer. Now it's the time to plug in. So this is just equal to tangent x cubed plus 2 to the fourth e to the 5x times the whole expression that we just found for the derivative. And then you do whatever you need to do with this if you want to simplify it. Let's not do that though. Most problems involving complicated derivatives like this will just tell you find the derivative, no need to simplify. But you could, for example, when you distribute this into the first fraction, tangent has a sign in it that will cancel with the other sign downstairs. So there are simplifications that you could do. But this is a fine answer. So I'm going to move on to the next problem. This is the other typical function for which you actually need log differentiation. We've talked about how this one, we don't know yet how to differentiate this, x to the x. I told you that you don't use the power rule for this. The power rule differentiates expressions where the variable appears as the base. This is the power rule. And the exponent rule, you can call it, or derivative of the exponential function, is when the variable appears only as the exponent. We also know how to differentiate that. But in this case, you have the variable in both places. You cannot use either of these rules. We're not going to use that. So what do? We have no choice here, but to find, if you take a log of this expression, it becomes simpler because it is a exponent. So that's what we're going to do. F of x is x to the x. Ln of f of x is then ln of x to the x, which is x ln x. Okay, let me just do my usual color coding here. The exponent x is the one that came outside, whereas the one that was in the base remained inside of the log. That's how you take log of an exponent or exponential function. So now the derivative of ln of f of x, which on the one hand is always f prime over f, on the other hand will be the derivative of this expression, x times ln x. That's a simple derivative, just the product rule. I'm going to write this carefully. It's like this. The product rule works like this. You're going to need two terms added together, where in each term you have just one derivative in one of the functions. So x prime is 1. Ln of x prime is 1 over x. And you see that in the second term, you just get x over x, which is 1. So you found this. This is not your final answer. This is f prime over f. So f prime, the derivative that we actually wanted, is f times this, where now you plug in your original f. If you remember, that was just x to the x. This is the derivative of x to the x. By the way, it's only defined for positive x's. We should know this from the start already. We're taking logs of x. right? But even still, like when you have exponents involving variables, if your exponent is going to be a non-integer number, then the base is usually required to be positive. So this function is only defined for positive numbers x. Moving on. I have just one more of this, and then we can move on to implicit differentiation. This is similar to the previous one, just more complicated functions. F of x is now, again, a tower type of function. It's a function raised to another function. 1 plus x squared raised to cosine x. The logarithm of f, log of the expression on the right, is cosine times log of the base 1 plus x squared. I'm again using this power rule for logarithms. This is the one that we want to differentiate now. The derivative, which always on the one hand is f prime over f. On the other hand, will always be, will be in this case. How do you differentiate this expression? Well, first of all, it is a product between a cosine and then a more complicated function. So you need a power rule here. Sorry, a product rule, which I'm going to indicate like this. You see that in the first term, I differentiated just the cosine to get a minus sign. And then in the second term, we're going to need this derivative of ln of 1 plus x squared. So just like before, I'm going to right away write what this derivative is. But it requires the chain rule, right? It is log of an inner function. Try to think about what's going to be the derivative. The derivative of log applied to the inner function is 1 over that function. But you need to multiply this by the derivative of the inner function, which is just 2x. So now that's your chain rule again. Try to use the variable names y and u the whole process if you don't, again, if you cannot see this happening this quickly. But this is what you should find. Okay, so we have this expression. This is f prime over f. So solving for f prime, this is always the same. F prime is equal to f times, let me do dot 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 here, the expression that we just found. Because now I'm going to actually write down what the answer is by replacing this f of x with what it was originally. Let me circle this in orange and scroll back up. Here's your original f of x. 1 plus x squared to the cosine of x. So that's f of x times, and now the thing that I wrote as dot dot dot, well, now I'm going to actually write this down. Minus sine times ln of 1 plus x squared plus 2x cosine x. I'm multiplying the cosine inside of the red fraction over 1 plus x squared. I want to check my answer. Yeah, this looks right. That's f prime. Yeah, so I'm not going to do any examples where we then do things with the derivative, but the typical examples you should know already. It's like find the equation of the tangent line to a certain graph. There are many reasons to take a derivative, and we're going to learn more later. So you can expect problems that will ask you not just for the derivative, but will ask you to do something with it later. But we already know how that works. The focus today is just on finding these derivatives. So I hope this is clear enough. And there will be more problems in the recitation. But for now, I'm going to be moving on to the next topic. The next topic is implicit differentiation. It's again some context about taking derivatives, but it's not a different type of derivative or anything. How does this work? Well, before we talk about that, we need to talk about implicitly defined functions. So let's read the first item here first. When you have an equation like the ones that we have been having for functions, y equals f of x, you can say that this defines y as an explicit function of x. Because the variable y, the function, is isolated on the left side and you have only x's on the right. So it's an explicit formula that I give you as a function. Y is equal to x squared plus 2 or whatever. This is a function. But in many occasions, what you can actually find is what's called an implicit function. We're going to say that y is an implicitly defined function of x, or just implicit function of x, when you just have a relationship between x and y, but not in this form above. So I have many examples down here. Look at these. In all these equations, you don't have y isolated in one side of the equation and x is in the other. You have a relation between them. Like the first one we already know describes a circle in the xy plane, and the others are just more complicated relations. But any one of these relations implicitly defines y as a function of x. Even though you might not be able to solve for y in terms of x, like in here, this is a cubic equation. We don't generally have formulas to solve those. But that doesn't mean it doesn't exist. All right, the y can be still thought about as a function of x. So I have a quick problem here. What is or what are the functions y equals f of x that are implicitly defined by this relation? So in other words, try to solve for the function, for y in terms of x. This is a very easy problem to solve for y in terms of x. You basically just want to move all the x's to the other side. 25 minus x minus 2 squared. Now you can take square roots. This is though gonna require having a plus or minus. You don't know the sign of the y minus 3 function. So in principle, this might be plus or minus. And you want to move the 3 to the other side as a plus 3. So you see that in this case, it was actually possible to solve explicitly for y, but you find two possible answers because of the plus or minus. So the two functions are now instead of y, you can call that f of x. It is a function of x. This expression using the plus, or f of x equals the same thing using the minus. And we can even discuss the domain of these guys if we want, because we have a square root. You want the thing inside of the square root to be larger than or equal to 0, but let's not worry too much about that. There are two functions defined by this expression. It makes sense, by the way, because this, and you look at the original equation, we should know that this describes a circle in the xy plane with a center at the point 2, 3. Looking at the translations here, minus 2, minus 3, and the radius of 5, which is the square root of 25. So you just have a circle here. Radius 5. You see that the circle itself is actually not the graph of a function, y as a function of x, because it fails this vertical line test. But there are two possible functions that it could be. It could be the upper half or the lower half. This is a function, and the one that's in red now is also a function. Those are the two ones that we just found. All right, so this is what it means to have an implicitly defined function. And what we just did here is the exception. It's not common that you can actually solve for it as an explicit function. In general, you cannot do that. Just another quick example for us to really understand what this means. Now, I'm telling you that y is implicitly given by this relation, this complicated relation that involves sine of y, y squared. We are basically hopeless if we want to solve this for y. There is no way to solve this explicitly. But that's not what they're asking. They're asking, what are the possible values for f of 2? Right, so y is f of x, and we want to know f of 2. Whatever it is, it must satisfy the equation. So we're gonna plug in x equals 2, and y is the number that we want. Y is the f of 2 because y is f of x. Those into the equation. Okay, so you see that the sine term that's multiplied by x minus 2 is gonna go away. And this final x in the expression is a plus 2. So what do you get? Y squared minus 3y plus 2 equals 0 for this particular value of y equals f of 2, the value that we want. Now this is a quadratic equation for that value, which is one that has two possible solutions, 1 or 2. Because it's an easy one to factor. So we have our answers here. F of 2 can only be 1 or 2 for this function, whatever it was. So in this case, we don't know what the original function is explicitly, but that doesn't mean that we cannot check for a few values of it. Sometimes we can. But if I had asked you for f of 3, that would be very different. That would be probably impossible to solve because plugging in x equals 3 would still leave you with the sine of y term. Right, so we have talked now about what it means to have an implicitly defined function. What we want to do now is find derivatives of functions which are given implicitly. That's called implicit differentiation. So this is not a different type of derivative, it is just derivatives. It just means finding dy dx, the derivative of y with respect to x, by taking the derivative of the whole implicit equation. And usually you're not going to be able to find an explicit derivative, you know, f prime, y prime equals function of x, but you're also usually going to find an implicit equation, something involving x's and y's all over, but that's okay. What's the only thing that you need to be careful about is that you must remember when you're doing this that y is a function of x, and the derivatives that you're taking are with respect to x. So you're going to be needing the chain rule for any expression involving y. Let me show you why. Literally, let me show you why. Here it is. Find an implicit equation for f prime of x if the function y equals f of x is implicitly given by this equation. So let's do this. Y is a function of x. We need to remember that. If you want, you should, I mean, at least when you're starting to work with this, you should replace all the y's in the equation with y of x. Just so it's clearer for you what's actually written in the equation. Because now when you try to find derivatives, let's find the derivative with respect to x. You will not say that the derivative of y squared is 2y. And you will not say either that it's 0. I mean, the original expression came from here, y squared. What is the derivative of this with respect to x? Well, it is not 0 because y is not just a constant with respect to x. It is a function of x. And it is not 2y either. You're not going to simply apply the power rule here. You need to consider that y is a function of x. You need the chain rule for this. So maybe this one I will do carefully. What is the derivative of this term, y of x squared? What is the dx of this? Or prime, if you will. Well, call the original, the whole thing, call it whatever you want, y of x squared, let's call that z, and call u the inner function y of x. So that z is just u squared. Find du dx, that's y prime or f prime, whatever you call the function, either y or f, that's irrelevant. And then the dz du is 2 times u by power rule. When you multiply the two together, that's the ddx of the z function that you wanted. So 2u times y prime of x, where u was equal to y of x. So this box here calculates the derivative in red up here, the derivative of y squared. It is 2y times y prime. That's what I'm going to write in place of that when finding the derivative. Now I'm going to scroll back up so we see the rest of the equation. Remember that we're taking the derivative of this equation right here. The next term is easy to find. That just involves x. ln of x, the derivative with respect to x is 1 over x equals. Now you need the derivative of this term, cosine of x times y, where y is a function of x. This is again the chain rule. So this time I'm not going to be as careful as I did down here. I'm just going to write this directly. But many of you will already have enough practice. The derivative of cosine of an inner function is minus sine of that inner function times the derivative of the inner function, which was x, y of x. How do you differentiate x, y of x? Maybe that fits in here. X times y of x prime. Well, that's the product rule. X prime times y plus x times y prime. X prime is 1, so you have it y plus xy prime. That's what goes in here. Okay, so this is the derivative of the original expression. I'm going to erase the x dependence now from the y and the y prime terms, just so it's a little bit cleaner. Usually we're not going to be writing the x dependence. I just did it in here so we remember that y is a function of x. We need to be very careful taking these derivatives. But this is the derivative of the expression that was given to us. Why did we do that? Well, remember that the question was asking for find an implicit equation for f prime, or that's the same thing as y prime, okay? F was called y in this. It's normal to call, instead of use the function f, if you have an implicit function, it's normal to find it called y instead of f. So we wanted to find an equation for y prime. This one right here is already an implicit one. So this is a final answer if you want. Like you can end here. Though in many occasions we actually want to solve for it in this equation. So I'm gonna go ahead and do that in here just to show you. This is not really a complicated equation to solve for y prime, because if you expand the parentheses in the second term, you have minus sine of xy times y minus sine of xy times xy prime. You see that this equation it has a bunch of terms containing y prime and a bunch of terms not containing it. So move all the y primes to the one side and factor the y prime. So on the left side, I have everything that had y prime, and I factored the y prime. And on the right side, everything that did not have y prime. I forgot an x here, right here. This term has an x. That's where this new term here came from. All right, so solving for y prime means now just dividing by this factor of 2y plus x sine xy. In many occasions, you actually want to do this. So I'm now finding an explicit formula for y prime, except it's not really that much explicit because it still has y inside of it. But we don't know what the function y is in terms of x. That function was given implicitly. But as long as we have a few values for the function and also the x, we should be able to find some values for y prime using this formula. So this is you can still call this implicit because there is no formula involving only x's. this is an expression that you can find. So what I want to do is do more examples like this. Here it is, the next one. Find an implicit equation for dw dt if the variables w and t are related by this expression here, w over t equals ln of w. Well, okay, what is the independent variable? It's t, the one that had the rule of x in the previous example, because it is the one with respect to which we are taking a derivative. That's how I know. T is the independent variable, and w is a function of t, because I'm taking a derivative of w with respect to t. So we don't know how to solve for w in terms of t from this equation. It involves w and also ln w. It's not possible to solve, but we can take derivatives of this. So the equation, again, I'm going to write the t dependency. You should do this at the start so you know exactly what is a function of t and what is not. And now you can try to take a derivative. Derivative with respect to t. What is the derivative of this equation? On the left side, you have a quotient rule. So that's the low d high minus high d low. Well, t prime is 1 over t squared, low squared. And on the right, that's the chain rule. I'm already going to write down the answer here. I mean, we know this from the previous topic of logarithm differentiation. Remember, ln of f, when you take prime of that, you always find f prime over f. That's a similar thing here. So at least I'm going to indicate this was obtained by the chain rule. Very good. Next, I'm going to erase the t dependency, so we don't worry about that. This t prime here is equal to 1, by the way. So you really had this simpler thing on the left side, t w prime minus w over t squared, and on the right it is w prime over w. Okay, this is an implicit equation for w prime. This could be your answer, but I would not encourage you to leave it like this. I want you, I'm saying this because I don't know what the exam is going to ask for. It might be that they actually want you to just completely solve for w prime in terms of w and t. If they just say implicit, it's not so clear what they mean, but let's solve for w prime from here. How do we do that? So first of all, I'm going to separate the things that have a w prime and the things that don't have. I'm going to start by cross multiplying everything. Like this. I just cross multiplied, and I'm going to distribute this little w inside. So w prime t minus w squared equals t squared w prime. Let me move all the w primes to one side and factor. And all the things that don't have w prime on the other side. So this guy, t squared w prime, came to the left. And here it is, t squared w prime with a minus sign. The other term on the left is this one, w prime t. Here it is, factored a w prime from it. And finally, this minus w squared is now on the right side as a plus. So now you can divide by wt minus t squared. That's your implicit formula for w prime, or which is the same thing as dw dt as the question asked. So let me do one more of this. This one is kind of a trick question. I'm giving you an implicit relationship between x and y that cannot really be solved very satisfactorily, at least. I mean, you have to use inverse trig functions, so let's not do that. But they want an implicit differentiation, but look at this. It is x with respect to y. So this question is here as a trick question. Usually y is a function of x. In this case, x is a function of y. Y is independent because it is a derivative with respect to y. And x is a function of y. You can say like this, x is equal to x of y. X is a function of y. That's a way to write that. So when you rewrite your equation, it is like this: sine of x of y plus sine of y equals 10. You want to find derivatives of this equation with respect to y. How does that work? Well, this first term is the chain rule. I'm just writing that again quickly. Chain rule. Derivative of sine is cosine, and derivative of the inner function is x prime of y. Plus, what is the derivative of sine of y with respect to y? It is cosine of y. Equals. Try to not write a 10 here. The derivative of 10 is 0. That is just a constant. Now I'm going to erase the y dependency. Really, you just have cosine x times x prime plus cosine y equals 0. The thing that we wanted to find is x prime dx dy. All right. So I'm going to solve for that. That's an easy one. If you move the cosine y to the other side first as a minus cosine y, and then divide by cosine x, then you have it. This is an implicit formula for dx dy. Last one. With this one, we're going to do something more than just the derivative. But it's really not that big. So I'm telling you, the circle of radius root 5 centered at the origin has this equation. We should know that. So in this problem, we are talking about this circle, radius root 5. Item A is saying verify that the point 1, 2 belongs to the circle. 1, 2, this point. How do we know it belongs to the circle? That's very easy. Given the equation of the circle, the points on the circle are the ones that satisfy that equation. And that's true for the point 1, 2. If you're talking about the point 1, 2, x coordinate 1, y coordinate 2, you can check it is true that those two numbers 1 and 2 satisfy this equation. Right, so the point is on the circle. That's the easy part. This is again testing the meaning of if you know what an implicit function is. And now we want to find the equation of the tangent line to the circle at that point. Okay, so in B, we're trying to find the equation of this line in red right here. You can see that it's going to have a negative slope just from the picture. Now, well, usually we want to think of y as a function of x, which is the case. All right, this around this point here, it is true that you can think of y as a function of x. It is not true all over the entire circle. Y is definitely not just one function of x. But around that point, it is like it's like you're taking the upper half of the circle, this one. But you don't need to find that explicitly. That's the whole thing here. We're going to say that y is a function of x. And we're going to use the equation, which is x squared plus y squared equals 5. Use this to find the derivative y prime of x. We need that if you want to find this tangent line. So now it's a matter of implicit differentiation. Derivative of x squared is 2x. Derivative of y squared is 2y y prime. Again, that is the chain rule. I'm always going to indicate this. And we should all know how to do that. Derivative of 5 is 0. So solving for y prime here, I guess we can divide by 2 first. x plus y prime equals 0. So moving the x to the other side and then dividing by y, you have y prime is equal to minus x over y. This is the derivative in terms of both x's and y's. Now, okay, the tangent line at the, let's say, a point a f of a. A general formula for the tangent line is always like this. F prime of a is the slope, and the coordinates a and f of a appear like this. This is the equation of a tangent line. So the three numbers that we need to know are always a, f of a, and f prime. Well, we know what those are. A, f of a is the point given on the graph, x coordinate 1, y coordinate 2. But what is f prime of a? Or I guess I never called it really f. The function is y. Y is a function of x. And the number a is the x coordinate 1. What is y prime of 1? Well, even though we don't know the formula for y explicitly in terms of x, we just found its derivative up here. The derivative is always x over y with a minus sign. So that's the formula that I'm using, minus x over y, where x and y were obtained from the point 1, 2. Okay, so those two things are giving me this minus 1/2. That was the whole point of this problem, like using the implicit differentiation formula and then actually putting it to some work, actually applying this formula. And as I said, by the way, this is a negative slope. By looking at the picture, we knew this had to be a negative slope. So you have your answer, y minus f of a is equal to minus 1/2 x minus a. That's the equation of the tangent line to that circle at that point. All right, so recitation will then involve more problems like this one, where you're not only finding an implicit differentiation, implicit derivative, but you're also putting it to use. So look forward to those problems in the recitation and the exam, of course.